What is the main focus of the paper, based on the introduction section?
The main focus of the paper, based on the introduction section, is to explore how in-context learning works in computer vision, specifically in the context of visual in-context learning, (ICL). The paper aims to investigate the existence of visual task vectors in computer vision models, similar to the task vectors found in natural language processing (NLP) models. The study is inspired by previous research in NLP that suggested the presence of task vectors and function vectors in large language models. The paper seeks to understand how visual ICL operates in computer vision models, particularly in the MAE-VQGAN model, and proposes a practical method to identify and utilize visual task vectors to guide the model towards performing various downstream tasks without specific fine-tuning. The paper also delves into the integration of causal interventions and activation patching to elucidate the decision-making processes of complex neural networks in computer vision.
How does the paper propose to explore in-context learning in computer vision?
The paper proposes to explore in-context learning in computer vision by investigating the existence of visual task vectors in the activation space of computer vision models. The study aims to understand how existing models can be adapted to different downstream tasks during inference time. The approach involves analyzing the activation space of the MAE-VQGAN model to identify task vectors that can guide the model to perform desired tasks without the need for specific fine-tuning. The paper introduces a method to score activations based on their ability to cluster data by tasks, indicating the presence of task vectors. By leveraging the reinforce algorithm, the paper outlines a process to identify and patch task vectors in specific locations within the model to guide it towards task performance. This method allows for zero-shot task implementation and demonstrates competitive performance compared to the original model, while reducing computational complexity. The study also includes experiments to validate the effectiveness of the proposed approach in various image-to-image tasks, showcasing improved performance over traditional methods like causal mediation analysis and greedy random search.
What is the significance of task vectors in the context of this paper?
The significance of task vectors in the context of this paper lies in their ability to guide visual ICL models to perform various computer vision tasks without the need for specific fine-tuning or changing model weights. Task vectors are latent activations derived from specific layers of the transformer that can be substituted for original latent states during the model's forward pass to direct it towards the desired task. By identifying and patching these task vectors into the model's activation space, the model can be guided to execute different downstream tasks effectively. The paper explores how task vectors can be identified in computer vision models, specifically in the MAE-VQGAN model, and demonstrates that by leveraging task vectors, the model can achieve competitive performance with the original model on a range of tasks while reducing the number of flops. This highlights the importance of task vectors in enhancing model adaptability, tailoring them to specific tasks, and gaining a deeper understanding of how different layers contribute to the model's overall function in the context of visual ICL in computer vision.
How does the paper propose to identify task vectors in computer vision models?
The paper proposes to identify task vectors in computer vision models by leveraging the activation patching methodology in conjunction with the reinforce algorithm. The process involves sampling random variables to determine whether mean task activations are considered task vectors, and then optimizing the parameters using the reinforce algorithm. By estimating the parameters theta, the sampling distribution p_theta is used to select the final task vector positions. The paper outlines a systematic approach to iteratively optimize the selection of task vectors by grouping potential patching positions into categories such as the CLS token, image patch tokens corresponding to the query, and mask tokens. This method allows for the identification of task vectors that guide the model towards performing specific computer vision tasks without the need for additional input-output examples, ultimately enhancing the model's adaptability and performance in a zero-shot setting.
What is the scoring mechanism used to evaluate task vectors in the activation space?
The scoring mechanism used to evaluate task vectors in the activation space is based on the concept of taskness. Specifically, the scoring mechanism computes the score row_token I for each activation, where I equals LMK represents the L_th block, M_th head, and K_th token in the model. This score is calculated by measuring the variance of the activations across all tasks compared to the variance within individual tasks. The mean activations for each position I and task J are also computed as mu_ij equals EZ_I_task_J. The scoring mechanism aims to identify activations that change significantly across different tasks, but remain consistent within a specific task, providing insight into the presence of task vectors in the model's activation space. Additionally, the aggregated per layer score row_layer L is calculated by summing the token scores within each layer, further aiding in identifying activations that capture task-related information.
Explain the process of finding visual task vectors via Reinforce as outlined in the paper.
The process of finding visual task vectors via Reinforce, as outlined in the paper, involves several key steps. Firstly, an exhaustive search over all subsets of activations is deemed intractable due to the complexity of the model, such as MAE-VQGAN with 32 blocks and 16 heads in each block. To address this, the Reinforce algorithm is utilized to identify task vectors. The algorithm involves sampling from a Bernoulli distribution to determine whether mean task activations are considered task vectors. These task vectors are then used to minimize the loss function, which is the expected loss over the sampled task vectors. The loss function is defined as the loss between the predicted output and the ground truth output, conditioned on the selected task vectors. The parameters of the sampling distribution are estimated through iterative optimization with gradient descent. Furthermore, the process involves grouping potential patching positions into categories such as the CLS token, the query image quadrant, and the mask tokens quadrant. This grouping reduces the dimensionality of the search space and simplifies the optimization process. The algorithm iterates over a set number of steps, sampling from the Bernoulli distribution to determine which positions to patch. The final task vector positions are selected based on the best evaluation on a held-out test set at intervals during the optimization process. This method allows for the identification of task vectors in a zero-shot setting, guiding the model towards performing desired visual tasks with competitive performance compared to the original model.
What are the key experiments conducted in the paper to validate the proposed methodology?
The key experiments conducted in the paper to validate the proposed methodology include 1. Activation scoring analysis. The paper evaluates the activation scoring step to determine if high-scoring activations correspond to task vectors. This involves collecting activations, computing mean activations and scores, evaluating clustering performance, and performing qualitative analysis through visualization techniques like T-SNE plots and heat maps. 2. Zero-shot task vector patching. The paper explores zero-shot task vector patching to assess if it can achieve task implementation performance similar to one-shot prompting. This experiment includes task-specific and multitask scenarios, comparing the proposed methodology to baselines like causal mediation analysis, greedy random search, random quadrants, random K-layers, and top quadrants. The performance is evaluated across various visual tasks like foreground segmentation, low light enhancement, in-painting, and colorization. 3. Ablations. The paper conducts experiments to validate specific design choices in the methodology. This includes investigating the impact of task vectors' location in the encoder versus decoder, as well as exploring different patching granularities, such as grouping tokens into quadrants or maintaining full token level granularity. These experiments help in understanding the optimal intervention strategies for effective task implementation. These experiments collectively provide a comprehensive validation of the proposed methodology, demonstrating its effectiveness in identifying and utilizing visual task vectors for in-context learning in computer vision models.
How does the paper compare the performance of the proposed method with baselines like causal mediation analysis and greedy random search?
The paper compares the performance of the proposed method with baselines like causal mediation analysis, CMA, and greedy random search, GRS, by conducting experiments on zero-shot task vector patching for visual in-context learning tasks. The results show that the task-specific models of the proposed method outperform the original MAE-VQGAN model across all tasks, while the GRS task-specific models even surpass the original model in some tasks. Additionally, the multitask models of the proposed method outperform the original MAE-VQGAN model in all tasks except for segmentation, where performance is on par, with GRS multitask models performing comparably to the original. On the other hand, CMA performs better than random baselines but does not achieve the high performance of the proposed method or the GRS method. The experiments also validate the importance of ranking layers by their activation scores and selecting the top K layers for the GRS method, as randomly selecting K layers does not perform well except for colorization where it is similar to GRS. Moreover, directly patching into the top quadrants without the iterative refining steps of GRS results in poor performance.
What are the ablations conducted in the paper to validate the design choices of the proposed method?
The ablations conducted in the paper to validate the design choices of the proposed method include two main experiments: task vectors location in encoder versus decoder, and patching granularity. In the first experiment, the researchers investigated whether interventions in both the encoder and decoder are necessary for task implementation. They compared the performance of restricting interventions to the encoder only, decoder only, and allowing interventions throughout the whole network. The results showed that both the encoder and decoder are crucial for task implementation, with the decoder playing a more significant role. This experiment aimed to understand the distributed nature of task computation within the model. In the second experiment, the researchers explored different levels of granularity for grouping tokens to reduce the dimensionality of the search space. They tested 3 granularity levels: individual tokens, quadrants, and heads. The results varied across tasks, with grouping by quadrants showing better performance in segmentation and colorization tasks, while maintaining full patching granularity at the token level resulted in better performance for low-light enhancement and in-painting tasks. These experiments aimed to optimize the patching process by finding the optimal level of granularity for grouping tokens.
What are the limitations mentioned in the paper regarding the proposed methodology?
The limitations mentioned in the paper regarding the proposed methodology include the focus solely on identifying task vectors, without considering other potentially important vector types such as image structure activations that capture locations, input-output placements, and left-to-right ordering. Additionally, during the optimization process with Reinforce, the evaluation of performance using the mean squared error (MSE) metric for all tasks, except for segmentation, which uses the mean intersection over union (MIOU), after decoding the predicted VQGAN tokens, may not provide the most accurate results. It is suggested that directly evaluating the model in VQGAN token space using cross-entropy loss could potentially lead to more precise outcomes. These limitations highlight the need for further exploration and refinement in future works to enhance the methodology's effectiveness and accuracy.